Puma Punku is located at 12,600 feet altitude in Bolivia, near Lake Titicaca. The site contains massive stone blocks, some weighing over 130 tons. These blocks were carved 1,500 years ago with remarkable precision. They're part of Tiwanaku, an ancient city that had 40,000 residents. The civilization thrived for 5 centuries, then collapsed around the year 1000. This is the story of what they built and why it disappeared. Let's start with the most striking evidence, the H blocks. These are the stones that made Puma Punku famous in archaeological circles and infamous in alternative history debates. They're scattered across the site now, displaced by some combination of ancient disruption, earthquakes, and modern reconstruction attempts. But their original configuration tells a story about capability. Each block is carved from red andesite, a volcanic stone with a hardness of 6.5 to 7 on the Mohs scale. That puts it in the same range as granite. Hard enough that modern stone carvers use diamond-tipped tools to work it. The blocks get their name from their shape. When viewed from above, they form an H pattern. 2 raised platforms connected by a channel, but the shape is only the beginning. Visual, camera moving along block surfaces showing geometric precision. What catches your eye immediately is the geometry. The surfaces aren't just smooth, they're planar, flat across their entire face. The edges aren't chipped or rounded, they're crisp, sharp. The angles aren't approximate, they're consistent. Block after block shows the same right angles, the same dimensions, the same proportions. And here's what makes it genuinely puzzling: the grooves. Each block has identical rectangular channels carved into its surface. Not similar, identical. The same width, the same depth, the same spacing, as if they were manufactured from a template. That's the word archaeologists keep coming back to: standardization. These blocks show evidence of intentional modular design. They were meant to fit together as part of a larger system, like components in the assembly. But here's the contradiction that makes this a mystery rather than just an impressive achievement. We have limited direct evidence of the exact tools used to create this precision. Stone tools and abrasives can work andesite. Experimental archaeology has demonstrated that. You can use harder stone hammers, diorite pounders, sand-based abrasives. You can peck away at the surface for hours, days, weeks. You can grind it down gradually, and that works. Modern experimenters have successfully replicated some of these features using ancient tool technologies. The surfaces can be flattened through patient grinding. The edges can be shaped through controlled pecking. But, and this is important, some features remain harder to replicate. The internal flat surfaces, the precision of the repeated groove patterns, the apparent speed of production suggested by the number of finished blocks. The experimental work shows what's possible with enormous labor investment. What it doesn't fully explain is the scale at which this was done, and the consistency achieved across dozens of blocks. If this were 1 or 2 special stones, religious objects, ceremonial pieces, the labor investment makes sense. But these blocks weren't unique treasures. They were structural components, building blocks. There are dozens of them scattered across Puma Punku, and archaeological evidence suggests many more were removed over the centuries, repurposed for colonial construction or lost entirely. That implies something remarkable. Tiwanaku had either a massive surplus of skilled labor to invest in geometric perfection for structural stones, or they had developed techniques that made this precision more achievable than we currently understand. The stakes here aren't small. If standardization and geometric precision at this level existed pre-Inca in the Andes, it means we've been underestimating the sophistication of centralized manufacturing and quality control in pre-Columbian America. It suggests workshop systems, training protocols, measurement standards, institutional structures that typically require writing to maintain across generations. But we haven't found written records at Tiwanaku, so either those records existed and haven't survived, or Tiwanaku transmitted complex technical knowledge through other means, visual templates, oral instruction, apprenticeship systems, that we don't fully understand. But before we can solve how they carved the stones, we need to address an even more basic problem. How did these massive blocks get here in the first place? The stones at Puma Punku come from 2 different sources, and that creates 2 separate logistical nightmares. First problem, the red sandstone blocks. The heaviest blocks at Puma Punku, the ones that weigh up to 131 tons, are made of red sandstone, The nearest quarry is approximately 10 kilometers away across rough altiplano terrain, 131 tons. To put that in perspective, that's roughly equivalent to the weight of 70 cars, or a fully loaded Boeing 737, or 20 adult elephants, except Tiwanaku didn't have elephants. They didn't have horses. They didn't have oxen or cattle or any large domesticated animals capable of pulling loads. The only pack animal available in the ancient Andes was the llama. A llama can carry about 25 kilograms, about 55 pounds. That makes them excellent for personal loads or trade goods carried along mountain trails. It makes them completely useless for moving stones that weigh 131,000 kilograms. The conventional explanation is human labor. Thousands of workers using ropes, wooden rollers, earthen ramps, and coordinated pulling. The kind of massive labor mobilization we associate with Egyptian pyramid construction or Easter Island Moai transport. And that explanation works, in theory. Experiments have shown that large groups of people can move extremely heavy stones using rope and rollers. The physics checks out. The leverage systems are sound. The problem is the archaeological evidence, or rather, the lack of it. When you move stones that size using ramps and rollers, you leave traces. The ramps themselves, massive earthen structures that have to support incredible weight, staging areas where work crews gathered, evidence of timber harvesting for rollers and levers, rope production waste, worker camps, food storage facilities. At Egyptian pyramid sites, we find all of this. The ramps, the tool marks, the bakeries that fed the workers, the housing quarters, the administrative records. At Puma Punku, we've found remarkably little direct evidence of the transport infrastructure you'd expect for moving 131-ton blocks 10 kilometers. Now, absence of evidence isn't evidence of absence. Sites get disturbed, organic materials decay, earthquakes disrupt archaeological layers, 1,000 years of weathering erases traces. But it's still striking. Either the transport system left minimal archaeological signature, or we haven't found the right locations to excavate, or the methods used were different from what we typically expect. And then there's the second problem, the andesite. Remember those precisely carved H-blocks we started with? They're not sandstone, they're andesite, that granite-hard volcanic stone. And the andesite sources are even more distant than the sandstone quarry. The nearest significant andesite deposits are on the Copacabana Peninsula, approximately 90 kilometers away. And here's what makes this particularly challenging. Lake Titicaca is in the way. That gives you two options. Either transport the stones overland, 90 kilometers around the lake through difficult terrain, or transport them across the lake by water. The water transport theory is actually more plausible than it sounds. Lake Titicaca's water level has fluctuated considerably throughout history. During wetter periods, the lake was higher and more extensive, and Andean peoples developed sophisticated reed boats, totora boats made from totora reeds that grow abundantly around the lake. Modern replicas of these traditional boats have proven remarkably seaworthy. Thor Heyerdahl's famous Ra-2 expedition crossed the Atlantic using a similar reed boat design. The technology can handle significant loads. So, it's geometrically possible that andesite blocks were quarried on the Copacabana Peninsula, loaded onto large reed boats, transported across Lake Titicaca, and then moved overland the final distance to Puma Punku. Possible, but unproven. We don't have direct archaeological evidence of the boat-based transport system that would be necessary. No ancient harbors clearly associated with stone transport. No stone cargo from sunken vessels. No depictions or accounts describing the process. Again, absence of evidence. But again, noteworthy absence. What we're left with is this. Two separate supply chains, one for sandstone, one for andesite, operating simultaneously over substantial distances, moving hundreds of tons of material to a single construction site at 12,600 feet altitude. That requires planning, logistics, labor coordination, staging, multiple work crews operating in parallel, supply systems to feed and house the workers, administrative oversight to manage the operation. In short, it requires state-level organizational capacity. And here's why that matters. When we think about state-level organization in the ancient world, we usually imagine bureaucracies with written records, clay tablets tracking deliveries, papyrus scrolls recording worker assignments, payroll accounts, inventory lists. We find those records in ancient Mesopotamia, in Egypt, in China, in Maya lowland cities. We haven't found them at Tiwanaku, so we're faced with a puzzle. Tiwanaku achieved logistical organization sophisticated enough to manage dual supply chains for monumental construction, the kind of complexity that typically requires administrative writing, but did so through organizational methods that either didn't use writing or used writing in forms that haven't survived, or used alternative information management systems we don't recognize. But moving the stones was only half the challenge. Making them fit together was the other half. Look closely at where these blocks were meant to connect. You'll see something that goes beyond stacking stones. These blocks have joints, deliberate, sophisticated connection systems designed to lock them together. Some blocks have projecting tenons carved from the same stone. Others have precisely cut mortise holes ready to receive those tenons. The tolerances are tight, the shapes are complex. Three-dimensional interlocking rather than simple flat-to-flat stacking. And then there are the clamps. Throughout Puma Punku, you'll find stones with carved T-shaped or I-shaped grooves. These grooves held metal clamps, copper or bronze, that were poured molten into the channel to secure adjacent blocks together. Think about what that means. Someone had to identify which blocks needed to be secured to which other blocks, calculate the positions for the clamp channels, carve those channels into both stones with alignment precision, pour molten metal to create the clamp, let it cool and solidify. That's not instinctive construction, that's engineered construction. It implies planning stages before the stones were even placed. It implies knowledge of metallurgy and its structural applications. It implies quality control, because if the channels don't align properly, the entire system fails. Some of the blocks show another intriguing detail, evidence of test fitting and adjustment. Tool marks that appear to be modifications made after the initial carving, slight chamfers on edges, minor adjustments to improve fit. What does that tell us? It tells us the builders weren't just following a fixed design carved in stone. They were iterating, testing, refining, making adjustments based on how components actually fit together. That's sophisticated building practice. It's what modern construction crews do when they're working with tight tolerances. Measure twice, cut once, and then fine-tune on site. But here's the contradiction. Medieval European cathedrals didn't achieve this level of pre-planned modularity until centuries later. Gothic master masons developed systems of standardized components and modular design, but they had centuries of accumulated knowledge, guild training systems, written architectural drawings, and geometric instruments. Puma Punku shows this same design philosophy 500 years earlier in a civilization without paper, without iron tools for precise measurement, without compasses or rulers that survived in the archaeological record. The standard explanation is that Tiwanaku refined these techniques gradually over generations, building on earlier Andean traditions of fitted stonework. And that's certainly part of the story. Earlier cultures like Chiripa did work stone. Coastal cultures developed their own masonry traditions. But the leap from modest fitted stone walls to modular megalithic construction with standardized components is substantial. It's the kind of leap that suggests either rapid innovation driven by particular individuals or institutions, or influence from outside contact, or a developmental sequence we haven't yet fully documented. There's another explanation worth considering. Specialized craft knowledge preserved through apprenticeship. Master stoneworkers training the next generation through direct instruction and hands-on practice. Complex techniques maintained through oral tradition and visual demonstration. This happens throughout history. Japanese temple carpenters preserve intricate joinery techniques without written blueprints. Pacific Island navigators maintain sophisticated wayfinding knowledge through oral teaching. Medieval European craft guilds protected trade secrets through apprenticeship systems. So it's entirely plausible that Tiwanaku stoneworkers developed and maintained sophisticated construction knowledge without writing. But here's the challenge with that explanation. Apprenticeship systems are fragile. They depend on continuity. Master trains apprentice, who becomes master and trains the next generation. Break that chain through disease, conflict, migration, economic collapse, and the knowledge can vanish in a single generation. Which brings us to a haunting detail scattered across Puma Punku: unfinished work. Some blocks have drill holes that were never completed, cutting marks that stop mid-process, rough surfaces that were never polished, stones that were clearly in progress when work ceased. It's as if the construction stopped suddenly, not wound down gradually over years, not completed and then abandoned, but interrupted. What could cause that? What could make an entire construction project halt mid-work? Before we can answer that, we need to understand why they were building with such precision in the first place. Because Puma Punku wasn't just a construction project. It was something with a specific purpose that required this level of engineering. From above, Puma Punku's layout shows something remarkable: alignment. The main platform is oriented to the cardinal directions: north, south, east, west, with significant accuracy, not approximate, not close enough, but carefully and deliberately aligned. That's not accidental. You don't achieve cardinal alignment by chance when you're building with blocks that weigh dozens or hundreds of tons. You achieve it through measurement, observation, and calculation. And it's not just Puma Punku. The larger Tiwanaku complex shows the same attention to astronomical alignment. The nearby Kalasasaya temple has gateway stones positioned to frame the solstice sunrise. During the winter solstice, the sun rises through one specific gateway. During the summer solstice, through another. This kind of precision requires sustained astronomical observation. You can't determine the exact solstice sunrise position from a single year. The sun's position on the horizon varies slightly from year to year due to atmospheric conditions and observation angle. To pinpoint the true solstice sunrise, you need to observe multiple cycles, record the positions, calculate the average, refine your measurements. In other words, you need data collection and analysis over multiple generations. Here's the contradiction. Achieving astronomical precision typically requires writing. The Babylonians tracked celestial cycles for centuries, accumulating written tables of observations. The Maya developed sophisticated calendar systems recorded in codices. Ancient Chinese astronomers maintained written records of eclipses and planetary movements. Writing allows you to record observations that exceed a human lifetime, compare data across decades or centuries, transmit precise numerical information without distortion, calculate complex alignments using documented methods. But we haven't found writing at Tiwanaku. No astronomical tables, no calculation records, no instruction manuals for achieving solstice alignments. So either Tiwanaku had writing systems that haven't survived archaeologically, perhaps on perishable materials like wood or textile that decayed completely, or they developed alternative methods for transmitting precise technical information across generations. Alternative methods like physical markers and monuments themselves serving as records, oral traditions encoding numerical and geometric knowledge, training systems that pass down observation and calculation techniques, visual systems using stone markers or other durable but non-written media. These alternatives are possible. Indigenous Pacific navigators maintained precise knowledge of star positions, ocean currents, and island locations through oral tradition and practical training. No written charts, yet they successfully navigated thousands of miles of open ocean. So the absence of written astronomical records doesn't mean Tiwanaku lacked the ability to track celestial cycles. It just means they did it differently than the literate civilizations we're more familiar with. But why bother with astronomical precision at all? Two explanations dominate academic discussion, and they're not mutually exclusive. First, practical agriculture. At 12,600 feet altitude, the growing season is short and unpredictable. Frost can kill crops in any month. Knowing the precise dates for planting and harvest could mean the difference between surplus and starvation. Astronomical alignments that mark the solstices provide a reliable calendar system. The summer solstice sunrise tells you the year's longest day has arrived. The winter solstice marks the year's turning point toward longer days. Combined with lunar observations and weather pattern knowledge, this gives you a sophisticated agricultural timing system. For a civilization supporting tens of thousands of people in a marginal environment, that precision has survival value. Second, religious and political authority. Astronomical knowledge demonstrates cosmic understanding, the ability to predict celestial events. To say the sun will rise through this gateway on this day shows mastery of cosmic order. That knowledge translates into political legitimacy. This isn't speculation. Throughout ancient world history, astronomical knowledge correlates with priestly or royal authority. Egyptian pharaohs used astronomical knowledge to legitimize rule. Maya kings recorded their births and coronations in relation to celestial events. Babylonian priests maintained power through eclipse prediction. Tiwanaku's rulers likely used astronomical precision the same way, as demonstration of their special knowledge, their connection to cosmic order, their right to organize labor and collect tribute. The two explanations, practical agriculture and religious authority, reinforce each other. The priests who can tell you when to plant aren't just useful, they're essential, and being essential translates into power. So the astronomical alignments at Puma Punku weren't decorative. They were functional, both practically and politically. They were part of the infrastructure that made Tiwanaku's high-altitude civilization possible. But here's what makes this story more complex. The astronomy requires long-term planning and institutional stability. You don't invest in multi-generational astronomical observation programs if you think your civilization might not exist in 50 years. You don't build monuments aligned to solstice sunrises that will only work correctly for centuries if you're thinking short-term. These alignments suggest confidence, continuity, expectation of persistence, which makes what happened around the year 1000 CE even more striking. Because that confidence, that expectation of continuity, was about to be shattered. But before we get to the collapse, we need to understand what else Tiwanaku built at its height. Because Puma Punku wasn't an isolated achievement. It was the centerpiece of something much larger. From the air, if you know what to look for, you can still see them. Faint lines in the landscape, regular patterns, the ghost of an agricultural system that once fed 250,000 people. The Suka Colas, raised agricultural fields. Here's what they look like. Rectangular raised platforms of soil, typically 1 to 2 meters high and 5 to 10 meters wide, separated by channels filled with water. The pattern repeats across hundreds, sometimes thousands of acres. You might think these are just primitive flood control systems. Raised beds to prevent waterlogging. Simple technology, you would be wrong. The Suka Colas represent sophisticated environmental engineering specifically adapted to the brutal challenge of high-altitude agriculture. At 12,600 feet, the Altiplano is one of the harshest farming environments on Earth. The problems are short growing season, frequent frost even during summer months, poor soil quality, unpredictable rainfall, high solar radiation during the day, but rapid heat loss at night. Traditional modern farming in this region struggles. Yields are low, crop failures are common, the margin for error is razor thin. The Suka Colas system addressed every one of these problems simultaneously through elegant engineering. Here's how it worked. The raised soil platforms absorbed solar heat during the day. The water in the channels also absorbed heat. At night, when temperatures plummeted, the water released that stored heat slowly, creating a microclimate around the crops. The temperature difference was enough to prevent frost damage on the raised platforms, while surrounding flat field crops froze. The channels did something else equally important. They provided habitat for aquatic plants and nitrogen-fixing organisms. This organic matter could be harvested and spread on the raised platforms as fertilizer. The system was self-sustaining, producing its own nutrients rather than depleting soil quality over time. The water channels also provided fish and waterfowl habitat, adding protein sources to the agricultural output, and they served as water storage, buffering against drought and ensuring moisture availability during dry periods. In other words, the Suka Colas weren't just raised fields. They were integrated agricultural ecosystems, combining crop production, soil enrichment, water management, microclimate creation, and supplementary food sources in a single engineered system. Archaeological evidence suggests that ancient Suka Colas fields produced 2 to 3 times the yields of modern conventional agriculture in the same region. Read that again. An agricultural system developed over 1,000 years ago, without modern fertilizers or pesticides or machinery, outperformed modern farming techniques in the same environment. That's not primitive technology. That's sophisticated environmental science. At Tiwanaku's peak, the Suka Colas network covered approximately 19,000 acres around Lake Titicaca. That's enough to support population estimates ranging from 250,000 to 500,000 people across the wider Tiwanaku state territory. But here's what makes this story tragic. The knowledge was lost. After Tiwanaku collapsed around 1000 CE, the Suka Colas system fell into disuse. Fields were abandoned, channels silted up, the raised platforms eroded. Local populations continued farming the Altiplano, but they used simpler methods with lower yields. For 1,000 years, people in the Lake Titicaca Basin farmed less effectively than their ancestors had. Think about that. A civilization developed agricultural technology so well adapted to local conditions that it tripled productivity. Then that civilization collapsed, and the knowledge vanished so completely that subsequent populations couldn't replicate it, even though the physical evidence was still visible in the landscape. It's as if medieval Europe forgot how to build stone bridges, and for 1,000 years afterwards could only cross rivers on wooden planks and rope. The modern rediscovery of the Suca Colis is actually an interesting story in itself. In the 1960s, archaeologists surveying the Altiplano noticed the patterns in aerial photographs. They identified them as ancient agricultural features but didn't fully understand their function. In the 1980s and 1990s, experimental archaeology projects attempted to recreate working Suca Colis systems. They rebuilt the raised platforms. They re-excavated the channels. They planted traditional crops. And it worked. The experimental fields demonstrated the frost protection effect. They showed improved yields. They produced exactly the results the ancient evidence suggested. For a while, there was excitement about reviving Suca Colis agriculture as a sustainable development strategy for Altiplano communities. Some projects successfully increased yields for participating farmers, but many of these projects eventually struggled or failed. Why? Because maintaining Suca Colis requires coordinated labor. The channels need regular cleaning. The platforms need periodic rebuilding. The water flow needs management. In ancient Tiwanaku, this labor coordination was organized by state institutions. When the state collapsed, those institutions vanished. Without centralized coordination, the system degraded. Modern experimental projects ran into the same problem. Without ongoing institutional support, funding, labor coordination, technical assistance, individual farmers couldn't maintain the system alone. The collective action problem proved insurmountable. That tells us something important about Tiwanaku. They weren't just building monuments. They were maintaining complex systems that required continuous organizational capacity. The state wasn't just political authority. It was functional infrastructure. And here's the deeper question. How did Tiwanaku develop this knowledge in the first place? The Suca Colis system is precisely calibrated to high-altitude conditions. The channel spacing, the platform height, the water flow rates, all of it optimized for the specific challenges of Altiplano agriculture. That optimization requires experimentation, trial and error, multiple iterations of build a field, observe results, modify the design, test again, accumulation of knowledge over generations. But there's no clear prototype phase in the archaeological record. We don't see crude early versions of Suca Colis gradually improving over centuries. We see the system appear relatively fully formed during Tiwanaku's expansion period. Either the developmental sequence happened somewhere we haven't excavated, or it was compressed into a shorter time frame than we'd expect, or Tiwanaku adapted and scaled up techniques that originated in other regions, all of which points to the same conclusion. Tiwanaku possessed sophisticated empirical knowledge about environmental engineering. They could observe natural systems, identify patterns, design interventions, test results, and refine techniques. That's the scientific method, applied not to abstract questions but to the urgent practical challenge of feeding people in a marginal environment. And the Suca Colis weren't the only engineered system keeping Tiwanaku functioning. The agricultural fields needed water, which brings us to another hidden achievement. Beneath Puma Punku and the wider Tiwanaku complex runs a network of water channels, not surface streams, underground aqueducts carved into stone. The channels are lined with precisely cut stone blocks. They maintain consistent gradients over considerable distances. They include junction systems where multiple channels merge. They feature settling basins where sediment could drop out before water continued downstream. In short, they're engineered waterworks comparable to Roman aqueducts, built at the same time as those Roman systems were operating, but on the other side of the world, in a civilization without iron tools or written engineering treatises. Water engineering is one of those technological achievements that looks simple until you try to do it. Moving water from point A to point B seems straightforward. Just dig a channel and let gravity do the work. But making it work reliably requires precision. If the gradient is too steep, water flows too fast and erodes the channel. If the gradient is too shallow, water moves too slowly and deposits sediment. If the channel isn't properly sealed, water leaks away underground. If the system lacks settling basins, sediment clogs the channels downstream. Tiwanaku's aqueduct network shows understanding of all these engineering challenges. The gradients are carefully maintained. The channels are properly sealed. The settling basins are positioned strategically. How did they achieve this without surveying instruments? The standard answer is they used the water itself. Build a test section of channel, let water flow, observe how it behaves, adjust the design accordingly. Iterative empirical engineering. That works. But it requires patience and multiple attempts. It means accepting that early sections might not work correctly and need to be rebuilt. It means accumulating practical knowledge through experience rather than calculation. There's another possibility. Tiwanaku possessed surveying equivalents that haven't survived archaeologically. Water levels, containers of water used as horizontal references, weighted plumb lines showing vertical alignment, measuring cords marked at standard intervals. All of these are simple technologies that wouldn't necessarily leave recognizable archaeological traces, especially after 1,000 years of decay and disturbance. Wood rots, fiber cords decompose, leather containers disintegrate. So we might be looking at absence of evidence rather than evidence of absence. Tiwanaku engineers might have had a sophisticated toolkit for measurement and alignment. We just can't find it after a millennium of decay. But whether through tools or through empirical iteration, they achieved results. The aqueduct system worked. It provided fresh water distribution to an urban population estimated at 20,000 to 40,000 people. That population density creates challenges beyond just water supply. You need waste management, drainage, prevention of waterborne disease, urban planning that prevents contamination of drinking water by sewage. Archaeological evidence suggests Tiwanaku addressed these challenges. The water channels are separate from drainage channels. There's evidence of waste management systems. The urban layout shows planning for sanitation. Again, this is sophisticated civic engineering. It's what makes cities possible rather than disease-ridden camps. And it's something else that was lost after the collapse. Post-Tiwanaku settlements in the region didn't replicate these urban water management systems. They operated at smaller scales with simpler technologies. But here's where the water engineering connects to one of Puma Punku's strangest features. Because the aqueduct channels don't just supply the city, they integrate with a water feature around Puma Punku itself that archaeologists have debated for decades. Look at Puma Punku from above and you'll notice something. The western platform is surrounded by what appears to be a moat or canal system. This raises an obvious question. Why would you build a water feature around a megalithic platform? Decoration, symbolism, or function? Some researchers have proposed something more intriguing. Puma Punku may have functioned as a port. At first, that sounds absurd. Puma Punku sits landlocked today, elevated above the surrounding terrain. The nearest major water is Lake Titicaca, several kilometers away. But Lake Titicaca's water level has fluctuated significantly throughout history. Paleoclimate evidence from sediment cores shows that the lake was higher and more extensive during certain periods. Local geology suggests that ancient shorelines existed at higher elevations than today's lake level. If the lake was substantially higher during Tiwanaku's peak period, roughly 500 to 1000 CE, it's geometrically possible that water reached or nearly reached Puma Punku. The moat system could have connected to the lake, creating a navigable channel. And this matters because Lake Titicaca wasn't just water, it was a transportation network. The lake connects highland and lowland zones. It provides access to distant resource areas. Reed boats, totora boats, made from local reeds, were sophisticated enough to carry substantial cargo. Archaeological evidence shows long-distance trade goods flowing through Tiwanaku, Amazonian shells from the eastern lowlands, Pacific coast materials from the west, minerals and textiles from various regions. If Puma Punku functioned as a port facility, it could have served as a redistribution center, trade goods arriving by boat, storage facilities at the platform, administrative oversight of distribution, tribute collection from subordinate regions. That would explain some puzzling features. The scale of the platform construction, the attention to water management around the structure, the complexity of the stonework suggesting high status function, the astronomical alignments indicating ceremonial importance. A port that was also a ceremonial center. A place where political authority, religious ritual, and economic administration intersected. But, and this is important, the port theory remains debated. Not all geologists agree that Lake Titicaca's water level ever reached Puma Punku's elevation during the Tiwanaku period. Some argue the moats are purely symbolic, representing sacred waters and the Andean cosmological concept of islands as particularly sacred places. In Andean cosmology, islands are powerful locations. They're liminal spaces between earth and water, between mundane and sacred. Many important Andean religious sites are actual islands, or symbolic representations of islands. Puma Punku's moat system could be creating that symbolic islandness without serving actual maritime function. The water represents cosmic waters. The platform represents sacred land emerging from those waters. The whole complex is a built metaphor for cosmological structure. So we have two competing interpretations, functional port versus ceremonial water symbolism, and the truth might be both. It could have been a working port facility that also carried symbolic meaning. Form following function doesn't exclude symbolic significance. The Romans built aqueducts that transported water efficiently, and they also made them beautiful, demonstrating imperial power and engineering skill. The practical and symbolic aren't mutually exclusive. What we can say with confidence, Tiwanaku was connected to far-flung trade networks. Exotic goods flowed into the city. That requires logistical organization, and water transport on Lake Titicaca would have been one of the most efficient ways to move bulk goods in the pre-Columbian Andes. Whether Puma Punku was literally a port or a symbolic representation of one, it was part of a system that extended far beyond the immediate site. Which brings us to the bigger picture, because Puma Punku wasn't a standalone monument. It was part of a massive urban center, a fact that took archaeologists surprisingly long to recognize. For much of the 20th century, Tiwanaku was classified as a ceremonial center. That term, ceremonial center, was used to describe sites that were thought to be primarily religious, places where people gathered for rituals and festivals but didn't necessarily live permanently, sacred spaces rather than cities. The logic seemed sound. Tiwanaku was isolated at high altitude. The environment was harsh. Surely this was just a pilgrimage destination where people came temporarily for ceremonies, then returned to their home villages? That interpretation was wrong. Systematically, definitively wrong. Modern survey using a combination of traditional excavation, ground-penetrating radar, and careful landscape analysis has revealed the truth. Tiwanaku was a city, a real functioning urban center with permanent residents, craft specialization, social hierarchies, and all the complexity that implies. At its peak, between 500 and 1000 CE, the core settlement covered 4 to 6 square kilometers. The population estimates range from 20,000 to 40,000 permanent urban residents, and that's just the core city. The wider Tiwanaku state territory included satellite settlements and rural populations that could have totaled several 100,000 people. To put that in perspective, 40,000 people is the size of a substantial medieval European city. It's larger than many cities throughout history, and Tiwanaku achieved this scale at an altitude where oxygen is 30% lower than sea level, where frost can occur in any month, where agriculture requires extraordinary ingenuity just to function. Archaeological excavation has identified specialized craft quarters within the city, metalworking areas with copper and bronze production debris, pottery workshops with kilns and clay processing facilities, textile manufacture zones, stone carving workshops, possibly including the areas where Puma Punku's blocks were finished and refined. This is what urbanization looks like. People who don't produce their own food, supported by agricultural surplus from the surrounding countryside, specializing in particular crafts or services, trading their labor for goods they need. It requires economic complexity, markets or redistribution systems, some way of connecting producers with consumers, administrative oversight to prevent fraud and maintain standards. The site also shows clear social hierarchy. The monumental architecture, Puma Punku, the Akapana Pyramid, the Kalasasaya Temple, these aren't communal village spaces. They're statements of power and resources. The Akapana Pyramid is particularly impressive. 257 meters wide at the base, originally standing approximately 18 meters tall, built from precisely fitted stone blocks, arranged in multiple tiers. It's not as large as the great Egyptian pyramids, but it's built at twice their altitude with more challenging logistics. That pyramid required millions of person-hours of labor. It required organizational capacity to mobilize and direct thousands of workers. It required surplus agricultural production to feed non-productive labor during construction. It required authority to compel or incentivize that labor. In other words, Tiwanaku was a state, not a chiefdom, not a loose confederation of villages, an actual state-level society with centralized political authority, economic specialization, social stratification, and monumental public works. Skeletal analysis of burials reveals multiple ethnic groups present in the city. Different skull shapes and dental patterns suggest people from various regions of the Andes lived in Tiwanaku. Some were likely merchants, some were craft specialists, some were political hostages or marriage alliance partners, some were conquered populations resettled for political control. This multi-ethnic character is another marker of state complexity. States expand beyond their core territories. They incorporate diverse populations, civilizations. They create cosmopolitan urban centers where different cultures interact, and we see evidence of Tiwanaku's influence spread across a wide territory. Artifacts in Tiwanaku style, pottery, textiles, metal objects, appear at distant sites throughout the Andean highlands and into coastal regions. That could represent trade, political control, religious influence, or some combination. Some of these objects are prestige goods, elaborate ceremonial vessels, fine textiles, sophisticated metalwork. These would have been markers of status, symbols of connection to Tiwanaku's power and authority. The city also had infrastructure beyond what we've already discussed. Monumental gateways, carved stelae depicting elaborately dressed figures, probably rulers or deities, sunken courtyards for public ceremonies, residential zones with varying qualities of housing reflecting different social classes. All of this requires something people often underestimate: knowledge. Technical knowledge, organizational knowledge, astronomical knowledge, agricultural knowledge, architectural knowledge, metallurgical knowledge, hydraulic engineering knowledge. Tiwanaku was a knowledge center, a place where expertise accumulated, where specialists trained apprentices, where innovations were developed and refined, where information flowed in from distant regions and was synthesized into practical applications. Before Tiwanaku, there was Chiripa. Chiripa was a culture that flourished in the southern Lake Titicaca basin roughly between 1500 and 100 BCE. They built small ceremonial platforms using local field stones, rough, unshaped, or minimally shaped rocks, stacked and fitted as best as possible. Chiripa architecture shows stoneworking skill. They could select appropriate stones, they could fit them reasonably well, they could create stable structures. It's respectable Bronze Age construction, but it's nowhere near megalithic precision. The blocks aren't standardized, the surfaces aren't precisely planar, there's no evidence of complex joints or metal clamps. The scale is modest. Platforms a few meters wide, not the massive scale of Puma Punku. Then Chiripa culture fades from the archaeological record around 100 BCE. There's a gap period, roughly 100 BCE to 300 CE, where we have limited evidence of major construction in the Lake Titicaca basin, and then Tiwanaku emerges. Somewhere around 300 to 500 CE, depending on which dating you use, Tiwanaku begins showing up in the archaeological record, and when it appears, it comes with megalithic scale construction, geometric precision in stoneworking, sophisticated copper and bronze metallurgy, urban planning, complex water management, astronomical alignments, and all the other achievements we've been discussing. That's a significant jump. From fieldstone platforms to geometrically precise megalithic architecture in, what? 200 years? 400 years? The standard archaeological explanation is developmental continuity. Techniques evolved gradually, each generation built on the previous generation's knowledge. Stoneworking skills accumulated through practice and innovation. Organizational capacity increased as populations grew and society became more complex. And that explanation is almost certainly correct. In broad outline, civilizations don't spring up overnight fully formed. They develop through accumulated learning. But here's the puzzle. We're missing the transitional phases. Where are the proto-Puma Punku structures? The attempts at precision that aren't quite successful? The experimental designs that show evolution toward the final form? The intermediate scale projects between Chiripa's modest platforms and Tiwanaku's massive complexes? They should exist. When we look at other architectural traditions, Egyptian pyramids, Mesopotamian ziggurats, Maya temples, we can trace developmental sequences. We see early attempts. We see innovations being tested. We see gradual increase in scale and sophistication. For Tiwanaku, that sequence is remarkably compressed or remarkably invisible. Several possibilities. First, the transitional sites exist, but haven't been found yet. The Altiplano is vast and underexplored archaeologically. Sites could be buried under sediment, submerged beneath Lake Titicaca's changing water levels, or simply located in areas that haven't been systematically surveyed. This is actually quite plausible. Archaeological knowledge is always partial. Second, the development happened faster than we typically expect. Maybe particular individuals or groups made rapid innovations. Maybe environmental changes or population pressures drove accelerated development. History isn't always gradual. Sometimes things change quickly. Third, external influence. Maybe Tiwanaku didn't develop entirely in isolation. Maybe contact with coastal Peruvian cultures or with other regions brought techniques and ideas that accelerated development. Trade networks existed, information traveled, technological diffusion happens. That third possibility is particularly interesting because there were sophisticated cultures developing elsewhere in the Andes during the same period. Coastal Peru saw the Mochi culture creating elaborate architecture and metallurgy. Ideas and techniques could have flowed between regions through trade, migration, or conquest. But external influence doesn't mean Tiwanaku was simply copying others. It means they were participating in wider networks of innovation and cultural exchange, something that's actually very common in human history. Most civilizations develop through combination of local innovation and borrowed ideas. What we can say with reasonable confidence, Tiwanaku represents a peak achievement of Andean highland civilization. They took whatever knowledge base existed, whether developed locally, borrowed from elsewhere, or some combination, and pushed it to remarkable levels of sophistication. They created an integrated system. Agriculture supporting urban population supporting specialized crafts producing tools and goods that enabled monumental construction demonstrating authority that organized agriculture. A self-reinforcing cycle of increasing complexity. And then, within a few centuries, something happened around the year 1000 CE. The precise timing is debated. Dates range from roughly 950 to 1100 CE, depending on which evidence you weight most heavily. But within that narrow window, Tiwanaku transformed from a functioning urban state to an abandoned complex. The archaeological evidence shows disruption, not gradual decline. Half-finished blocks with drill holes and cutting marks visible. Construction that appears to have stopped suddenly. Scattered displacement of stones. Though we have to be careful here because the site has been disturbed by centuries of earthquakes, looting, and modern reconstruction attempts. But even accounting for post-abandonment disturbance, the picture is clear. Tiwanaku didn't wind down gracefully over centuries. It collapsed relatively rapidly. Why? The most compelling evidence points to climate catastrophe. Sediment cores from Lake Titicaca show a severe megadrought around 1000 to 1100 CE. Pollen analysis, oxygen isotopes, and sediment composition all indicate a period of dramatically reduced rainfall lasting decades. At 12,600 feet altitude, agriculture is already marginal. Tiwanaku's whole system depended on careful water management through the suca colis and aqueducts. A prolonged drought would have devastated that system. First, crop failures, then food shortages, then population stress, then political instability as the state proved unable to manage the crisis, then breakdown of the organizational structures that maintained the infrastructure, then cascading system failure. This isn't speculation. We've seen exactly this pattern in other ancient civilizations. The classic Maya collapse correlates with severe droughts. The Bronze Age collapse in the Mediterranean involved climate stress combined with other factors. Climate doesn't determine history, but it creates pressures that human societies must manage and sometimes fail to manage. Tiwanaku's centralized system, which was a strength during good times, became a vulnerability during crisis. The complexity that allowed the city to support 40,000 people in a harsh environment required continuous maintenance. Break any part of that system, agriculture, water management, labor organization, trade networks, and the whole structure becomes unstable. Archaeologists call this complexity collapse. When systems become too complex and too interdependent, they lose resilience. A shock that could be absorbed by a simpler society causes cascading failure in a complex one. There's also evidence that population didn't simply disappear. People migrated, communities fragmented into smaller settlements. The urban center was abandoned, but rural populations persisted in the Lake Titicaca Basin, just at lower density and with simpler social organization. This pattern is important because it helps explain the knowledge loss. When a city disbands and people scatter into small rural communities, specialized knowledge can vanish. The master stone carvers, the astronomers, the hydraulic engineers, their expertise was maintained through urban institutions, through specialized training, through continuous practice on monumental projects. When those projects stopped and those institutions disappeared, the knowledge went with them. A generation later, no one remained who knew how to achieve the geometric precision of Puma Punku's H blocks. 2 generations later, no one remembered the exact techniques for maintaining the suca colis system. It's not that people became less intelligent. It's that knowledge is institutional. It's maintained through continuous practice and transmission. Interrupt that chain, and even sophisticated knowledge can vanish remarkably quickly. Think about modern knowledge. If global civilization collapsed tomorrow, how long before no one could repair nuclear reactors, build microprocessors, synthesize complex pharmaceuticals? Much of our current technical knowledge exists in specialized communities and would be lost if those communities dispersed. Tiwanaku experienced that loss on a civilization-wide scale, and once the knowledge was lost, it proved extraordinarily difficult to recover. For the next 1,000 years, no one in the Andean highlands built structures comparable to Puma Punku. No one achieved the agricultural productivity of the ancient Suka Kolus. No one organized urban centers of 40,000 people at that altitude. Not until the Inca Empire, which arose 500 years after Tiwanaku's collapse, did Andean civilization reach comparable levels of organizational complexity. And even the Inca, despite their sophisticated stone working traditions, didn't replicate Tiwanaku's geometric precision in quite the same way. So what's the pattern? What's the unifying thread connecting all these mysteries? Let's step back and look at what we've learned. Puma Punku shows evidence of geometric precision in stone, working achieved through methods we don't fully understand. Massive-scale stone transport requiring organizational capacity that left minimal archaeological trace. Complex joint systems, suggesting technical knowledge maintained without written records. Astronomical alignments requiring multi-generational observation, transmitted without written tables. Agricultural engineering more productive than modern methods. Hydraulic systems comparable to Roman engineering. Urban complexity supporting tens of thousands of people. All of this appearing relatively suddenly in the archaeological record, then collapsing rapidly around 1000 CE with significant knowledge loss. What's the pattern? It's not that Tiwanaku was impossibly advanced. It's not that they possessed technology beyond their time. It's not aliens or lost ancient wisdom or any of the fringe explanations that circulate online. The pattern is simpler and more profound. Tiwanaku achieved remarkable things through accumulated practical knowledge, but that knowledge was transmitted through systems that were fragile and dependent on institutional continuity. They were sophisticated empirical engineers. They observed, tested, refined, and applied complex techniques. They achieved results through skilled labor rather than advanced tools. They organized society effectively to mobilize resources for large projects. They developed knowledge through generations of accumulated experience. But, and this is crucial, they did it without some of the information preservation technologies that other ancient civilizations used. No extensive written records that we've found. No mathematical treatises. No architectural manuals. No astronomical tables. Their knowledge was embedded in practice, in oral tradition, in visual demonstration, in physical templates and monuments themselves. That works brilliantly when institutional continuity is maintained. Master trains apprentice. Successful techniques are repeated and refined. Physical structures serve as reference points for future construction. But when continuity breaks, through environmental catastrophe, political collapse, population dispersal, that kind of knowledge is vulnerable. It can vanish in a single generation. That's what makes Puma Punku remarkable and tragic simultaneously. It represents human capability at its impressive height, people solving extraordinary challenges through ingenuity and organization. And it represents human vulnerability, complex systems dependent on fragile continuity. The mystery isn't supernatural, it's historical and human. It's about the conditions that allow sophisticated knowledge to develop and the conditions that cause it to be lost. And here's what remains unknown. We still don't know the exact techniques used for the most precise stoneworking. We can propose methods, but we can't fully replicate the efficiency suggested by the scale of production. We still don't know exactly how labor was organized and compensated. How did Tiwanaku mobilize thousands of workers? Tribute, wage labor, religious obligation, some combination? We still don't know the full extent of their trade networks and external contacts. How much interaction was there with distant cultures? How much technology transfer occurred? We still don't know how technical knowledge was transmitted and preserved across generations without writing. What mnemonic systems did they use? How were measurements standardized? How were complex designs communicated? These aren't small questions. They're fundamental questions about how humans. New research continues to expand what we know about Tiwanaku and Puma Punku. Recent dating techniques are pushing back some of the timelines, suggesting earlier origins than previously thought. That might help fill in some of the developmental gaps we've been discussing. New excavations are revealing previously unknown structures. In 2025, archaeologists announced the discovery of an ancient temple in the Andes that sheds light on Tiwanaku's wider cultural context, showing that major ceremonial centers existed beyond just the core site. Underwater archaeology in Lake Titicaca is uncovering ritual offerings and submerged sites that expand our understanding of Tiwanaku's religious practices and possible water level changes. These discoveries suggest Tiwanaku's relationship with the lake was even more complex than we knew. New analytical techniques, trace element analysis of metals, stone sourcing through geological signatures, ancient DNA from skeletal remains, are providing details about trade networks, population movements, and resource extraction that weren't accessible to earlier researchers. Each answer raises new questions. Each discovery suggests more remains hidden. The Altiplano is vast. Lake Titicaca's waters have risen and fallen repeatedly. Sediment has buried ancient surfaces. Vegetation has overgrown stonework. Much of the region remains archaeologically underexplored. It's entirely plausible that significant Tiwanaku sites, or pre-Tiwanaku transitional sites, remain undiscovered. They could be beneath the lake. They could be buried under later settlements. They could be in remote areas that haven't been systematically surveyed. And that means the story we've told today is incomplete. The gaps we've identified might be filled by future discoveries. The mysteries we've highlighted might be resolved by new evidence, or they might deepen. More evidence doesn't always mean simpler explanations. What we can say with confidence is that Puma Punku and Tiwanaku represent a genuine achievement of ancient engineering and social organization, not supernatural, not impossibly advanced, but genuinely impressive and genuinely mysterious in the best sense of that word. They show us that human capability is both greater and more fragile than we often recognize. That people with limited tools and resources can achieve extraordinary things through ingenuity, organization, and accumulated knowledge, and that those achievements can vanish when the systems that maintain them collapse. Final visual, wide shot of Puma Punku at dawn, stones casting long shadows. The stones remain, the moats remain, the raised field patterns remain visible from the air, the aqueduct channels still run beneath the ground. What's lost is the knowledge, the specific techniques, the organizational methods, the practical wisdom that made it all possible. Puma Punku isn't impossible, it's evidence of what was possible and what was lost. And perhaps with continued research and new discoveries, some of that lost knowledge can be recovered, not to rebuild Tiwanaku, but to understand more fully the remarkable range of human achievement and the conditions that allow it to flourish or cause it to vanish into history.